Okay, welcome everyone for another quantum T section. And today I'm planning to still be talking a little bit about Bohm-de-Broglie interpretation of quantum mechanics. The focus will be more about spins, the new thing. But like about 10 days ago, something like that, I found this book here in a bookstore in Brazil. It's in Portuguese, but it has a David Bohm book. But I will write the title in English because originally it's in English. So it's the wholeness and the implicate order. It's I start reading and I felt it's a very
Hello. I think you
yeah
cut off for a little bit, but you're back.
yeah I'm back. Yeah, okay. Yeah, I receive a message and the implicate order by David Bohm. It's a book from the 80s, 1980. I have the version in Portuguese because I found here. I don't know if people from YouTube can see the message, so I will share the screen. Okay, so this is the book, the title of the book, and this is a very nice, like Diego web page in YouTube. There's a lot of very nice videos about um, quantum physics and quantum physics experiments, right? And yeah, and this is the book again. This is in the Portuguese version, but the title in English is this one. You guys can find. I start reading this book. It talk a lot about a lot of things, including like consciousness and all these things. I'll not talk about this, at least not for now. But in the chapter 4, it has like a summary of the ideas from Bohm de Broglie interpretation of quantum mechanics, and this summary I thought it's very good and very clear, better than in the original paper. So that's why I recommend it here. So I'm thinking like to make a review, a summary of the things that we saw uh, until here about the Bohm de Broglie interpretation, and then we'll talk a little bit about spin. That's the new things that we still didn't talk about. So okay, so let's start. This is the third section, the video section about the Bohm de Broglie interpretation. And let's make a summary for the things that we saw so far. This is the quantum mechanics interpretation in terms of hidden variables. So today we will first review what we have discussed in the previous sections about the Bohm de Broglie proposal for new interpretation of quantum mechanics in terms of hidden variables. Then we'll discuss how this proposal interpreted the existence of spin of the electrons in quantum mechanics. So as emphasized by David Bohm in several references, these proposals are preliminary, and the main goal is that they might be considered as a starting point in the development of more detailed theory. So the main points can be emphasized in the following postulates. So this is the summary from the things that we saw until here about Bohm de Broglie. So the wave function can be represented in this way, is assuming as representing a real and objective field, where R and S are the amplitude of the field and S is the phase, are both real. And and at the amplitude in the phase. Yes. And it's supposed that together with the field, this field here, psi, there is a particle represented mathematically by well-defined coordinates that vary in a definite way. The third point is it is assumed that the velocity of the particle is given by an expression like that, where m here is the mass of the particle, and s is given by the field psi. It's supposed that the particle is influenced by a classical potential, like in the usual quantum mechanics, V. If for instance, this potential could be like a Coulombian potential. But adding to this potential, there exists another potential that's called a quantum potential. That's given in terms of this expression here, in terms of the R is present in the field psi. And finally, is assumed that the field psi is in a state of fast random oscillation in such a way that the psi values are a type of average in a certain characteristic time tau. Such interval tau must be long when compared with the quantum mechanical processes. And the fluctuations of the field psi could have originated from a much deeper sub-quantum mechanical level. So what he means, like he gives an example. The example David Bohm gives is like in the Brownian motion, when you have like imagine you put like a dust in a fluid like water, some water. This dust will like have like random motion that is called Brownian motion. Yeah. And this motion is due the influence of the molecular or atomic nature of the fluid. But when this was like observed for the first time, like about 200 years ago, you could like see the the particle nature of the fluid, and you could see the atoms and the molecules in the fluid. So you have like something that was like subatomic that make the dust have this type of random motion when in a fluid. So the same thing, like this is just an example. So Bohm suggests the same thing could happen here. So the fluctuations, the original fluctuations of the field psi could be something that is subquantum mechanical level, something that we can't see yet. And when he proposed this was in the 50s, like 70 years ago, but we can't see this effect. If this is right, we can see this effect even today. So okay, so the field beside has this like random oscillation that we don't know exactly what it is.
Carlos, when you say sub quantum mechanical level, all right, we got subatomic electrons, protons, things like that.
Yeah, something like that.
What scale are we looking at subquantum?
Yeah, so probably smaller. But I think David Bohm, he suggests something like 10 to the minus 13, I think, in the papers, meters.
So it is an actual size range that we're looking at.
Yeah. At least in the 50s, when he suggests this, I think it's 10 to the minus 13.
Thank you.
Okay. So this, like 5 postulates. So taking into account these postulates, let's consider that the field psi oscillates in equation 1, that's the equation for the field. No, equation 1, that's the equation for the velocity, this one. Implies that the fluctuations will be communicated to the particles movement through the quantum potential UQ. That's the equation 2. In this case, the particle will not follow a regular trajectory. Instead, it will have an irregular path. And in this path, the particle will possess a velocity given by averaging equation 1, the equation for the velocity, in terms of the field fluctuations that occur during the interval time. Thus, it's possible to show that these random motions will guide us to consider that the field psi gives rise to the probability density given by this expression. Okay, where this dV here is the volume element where the particles are taking the random movements. Thus, psi can be interpreted as determining the motion of the particles from equation 1. This motion of the particles in equation 1. The quantum potential, equation 2, and the probability density, equation 3. So in some sense, like the psi is involved in all the field is involved in all the parameters, extra parameters here in this interpretation. It's also possible to show that such a theory has the same results previewed by the non-relativistic quantum mechanical orthodox interpretation. However, this is done differently in terms of the existence of a deeper knowledge about nature's law. That's now the things are like totally deterministic, right? Because the Schrödinger equation is deterministic, but it's when you solve, you are relating to these parameters here. That, for instance, you can like determine the trajectories of the particles. So one example for this is that we already discussed the double slit experiment. Here you have the like a representation for the double slit experiment in views of the de Broglie and Copenhagen interpretation. Like here, in terms of the Copenhagen, the
I guess we lost Carlos.
Yeah, it seems like it.
Yeah. I guess we'll just have to wait for him to come back. Hey, Barry, I know she got 2 connections now. And if you're talking, I can't hear you, Barry.
Diego, could you post that link again?
Yeah, I can still see it in the chat there. I'll repost it.
I can't see it because I just joined on this machine. There we go.
Let me know if you see it.
Got it. Okay, great. Thank you.
Yeah, of course, you're welcome.
Hey, Diego Invesso. I know Barry and I are from New Jersey. Where are you guys from?
Oh, good question. Originally, I'm from Colombia in South America,
Okay.
but I'm located in Atlanta right now.
Okay.
And I'm also originally from Europe, but I'm located in California.
Okay.
Where you said that you are now, Bob?
I'm right outside Philadelphia in Haddonfield, New Jersey,
Uh,
and I think Barry's a little further north of me.
mhm.
Um,
Hmm.
So the third person that usually pops up from our area is George Ziflin, and he's from Philadelphia proper.
Mm.
There's like
So
a couple
there's a
of
big Philadelphia
Yeah.
probability wave function.
in quantum formalism, you got me, Barry, George, and the gal that's doing the elliptic curve cryptography courses from Penn, also in Philly.
Wow.
That's why sometimes I joke when the people ask where do I live, where I'm from, and I said, well, my wave function spread out all over the world nowadays.
Yeah.
Actually, I came back, on Friday, came back from Europe. So now just adjusting with all the other schedule. Because when I was in Europe,
Okay.
this was coming in the evenings when all the events were happening. Now it's
Right.
in the morning, which is a time that I could try to shield and attend.
Right. So you're first thing in the morning. We're like lunchtime.
Yeah.
And Diego's lunchtime too, I guess. It's 1:00, 1:30 right now. East
Yeah.
Coast.
Yeah, it works really well for me on Tuesdays, but I haven't been able to go on the Friday class, attend the live session in a while. So I have a conflict there, but I
Okay.
try to watch the YouTube videos.
And I think I've seen you guys in the Physics with Friends. Is that right?
Yeah, we were in the programming one that Dimitri runs.
Yeah. Yeah.
Yeah. We've seen you in so yeah.
I'm not familiar with that one. Is that also from? Is that part of quantum formalism, or is that
No,
separate?
this is more like California stuff. Yeah,
Oh.
meet up with people started from California,
Mm.
and I think the one that you said, Dimitri, that was the quantum that I was running before the pandemic and during the pandemic.
Mm.
And then after the pandemic was over, I had to travel. I went back to Europe, and so I dropped the ball there and said, well, I cannot handle it. Then I have to travel, and so I'm glad that he picked it up.
Yeah, yeah, and right now they're kind of trying to decide what they want to do in the future with it. Yeah, we
Yeah.
were going through Nelson and Sean. We got to chapter 8.
Oh,
A lot of it was like wound up being like only 3 of us, maybe 4, that were actually doing anything in chapter 8. So
Yeah.
I
Well,
would
I
have
found that
enjoyed doing
Carlos
that.
is actually giving a very nice kind of fundamental overview about quantum mechanics.
yes,
Yeah.
and in some ways, Carlos's course is nice because the one thing we skipped in the Physics with Friends computing course was chapter 7, which is the hardware chapter,
Yeah.
which Carlos is doing. So, you know,
Compliments so well.
yeah, it worked out well for everybody. And I know that guy Wayne, who was part of the computer group, his good friends, is now doing representation theory.
Mm-hmm. Yeah.
Yeah, which is kind of an offshoot of the computing side.
All right.
I'm back.
You're back.
So exactly where I stopped. I collapsed. I don't know exactly where I stopped, so it's still recording. Yeah.
Are you? I think you're frozen.
Yeah. Where? Let me share here. Let me show these slides. You guys tell me where I stopped. Well, this you guys, I believe you didn't see, right?
Yeah, we were around
Stop
here.
right there.
Here?
Yeah.
You guys saw this?
Mm-hmm.
So, okay, so you want to continue from here, or you think is better? What you guys?
Yeah, continue
you guys
from there.
from here. So, okay.
Yeah.
So let's see if it works now. So this is we already like showed this in past. Like this is double slit experiment. You have here in this interpretation, like the Copenhagen time and the versus the Bohm-de-Broglie interpretation. So the particle here represents like the particles that come in the Bohm-de-Broglie interpretation, the particles that come in like in the top side of the slit. The slit in the top has these trajectories, that's random trajectories, and in the bottom, the particles that come in the bottom slit has these trajectories here. So it's not the particle, let's say the electron here, now is not a wave that come from these two slits and have like that wave behave, like in the Copenhagen interpretation. What we have here in the Bohm-de-Broglie case is that the particle follows a definite path, but with a random trajectories. And this type of behavior is a psi-dependent. Psi is the field. So the places where the particles are detected by the apparatus are determined by several factors. Some of them are here. So the particle initial position, the initial form of the psi field, the changes in the psi do the slit if influence, and the random changes in psi from subatomic origins. So in a statistical analysis of all cases, the fluctuations of the psi field would reproduce the same usual interpretation of quantum mechanics. But here, like the probabilistic interpretation, this statistical analysis here comes from like in the same way as we have like in the classical world. Like for instance, like if you want like to make up to know the what will be the weather like tomorrow, we have the probabilistic preview, but because we don't know like all the parameters that we have now to make like a exact prevision. So you have this like a probabilistic interpretation in this case is like in the classical field. So it's the same thing here. Okay, so we have this statistical analysis that we have, and we have like a probabilistic interpretation in the end. But this probabilistic is like in the classical worlds that we know, statistical physics that we use like in daily. And one of the reasons that we don't know the field psi is random due to some subatomic origins that we don't know about. So okay, and another example that we want to discuss here is the spin of the particle. And we see that we have like the same interpretation. So I'll take this paper here, this physical letters A from 1996 from these guys here, and basically what they do, seeing this red part here, is according to such an interpretation, like the Bohm de Broglie interpretation, we may assign well-defined trajectories and spin vectors to particles, and study how these interact with the apparatus during the course of measurement. For a spin measurement, the conventional collapse of the wave function, that's like in the Copenhagen interpretation, onto eigenstates of spin operators along the field direction is replaced by a continuous evolution of particle spin vector toward either alignment or anti-alignment with the field direction. So continuing here in this part, in this letter, we provide a fully relativistic account for similar spin measurement. And our results demonstrated that the deterministic evolution of the wave function suffices to account for the discrete outcomes of a quantum spin measurement. And here he says what did he do exactly, like in part 3 of the paper. Suppose we wish to measure the z component of the spin of uncharged spin 1.5 particle, and we observe the deflection of the particle after passage through an inhomogeneous magnetic field directed along the z coordinate axis, and so infer the component of the spin along the field direction. So exactly like in the Stern-Gerlach experiment. And he considered like a wave function of this type, where this sigma 3 here is one of the Pauli matrices. I think it's the Z matrices. Okay, we have some questions? No? Comments?
Yeah, you mentioned that
Yes.
the quantum interpretation of this traditional is that it would collapse that the state of particle would collapse the eigenstates.
Yeah, this is the conventional. Right? This is the
Right,
Bohm interpretation, the Copenhagen interpretation.
Right.
We have like a superposition of spin up and down, and then the wave function collapses from one of them.
Right. With this new interpretation, are we still collapsing to the eigenstates?
Yeah, in this interpretation now that you see here, you have this behavior. So this you have like initially the wave function. Here is an example where he put like half of the spin of the particle has a spin up and half of the particles has a spin down.
Okay.
And this is the wave function representation here is symmetric. Here is distance in angstrom here. Okay, but this is the spin that has the particles that has a spin oriented like up will follow. This is a Stern-Gerlach experiment, the inhomogeneous like field, magnetic field, and half of them that has a spin up goes in this trajectory, like in the positive axis here.
Okay.
And the particles that has spin like down goes in this trajectory, in the negative axis here. And here is like the spin vector field from this type of experiment. So half of them up and half of them down. Okay, here's the time, 10 to the minus 14 seconds. If this is too small, I can show in the original paper that it can make it bigger. So just to see very quick here. So the equation of motion of the particles with spin plus and minus 1.5 is given by an expression like this. So it's a type of Schrödinger equation with this extra term here, that where mu is the magnetic moment, h is the magnetic field, and sigma ij are the components of the three Pauli matrices, x, y, and z, that usually we use in quantum computation. Psi I is a Pauli spinor parameterized in this way. So we have two components here. Psi I is this two here that he used to make the model. And with the velocity, you can like calculate the Bohmian's trajectories. The Bohmian's trajectories as a typo here. The Bohmian's trajectories were evaluated using equation 6. This one here. Yes, and then this. And basically this thing. So you now have like definite trajectories. So the particle has a spin up or down initially. And then when they go to the Stern-Gerlach experiment, it has the trajectories like this. So they are not the spin is not a thing that is in superposition now, and the wave function collapse like in the usual interpretation. Yes, well, we have this problem with internet, but I hope you cannot like lose the idea.
Can you go back to that plot that was showing the evolution of the spin? I'm just a little confused. Catch the one that shows that half of them are going spin up, half of them spin down.
In this one, the figures?
Yeah, that one. So
yeah,
that's time. So and then the y-axis, what is it? Is the z coordinate?
Oh, this is time, and this is the z coordinate. Okay.
Yeah.
Z in angstrom, the unities.
I was trying to see what figure C was.
C, this is time, and this is z.
That's the evolution of the spin vector projected. But why is it that the ones in the middle, it seems that some of them are still not decided for spin up or spin down? So what if you take a measurement, let's say at, I don't know, 0.5 seconds, or e to the minus, I know it's probably impossible to make a measurement at minus 15 seconds, but that would imply that the spins are not the measurement wouldn't be an eigenstate.
Yeah, at least in this here, it's because here, if you take like 1.5, it seems that they go up. But here, as you said, it seems they have like not decided if they are up or down.
Yeah.
Right? It's a little bit confused here.
Yeah, and that's, I think that part is, to me, is confusing, because that would mean you would get, let's say on a Stern-Gerlach experiment, you would get some particles that are not either deflected upwards or downwards, but somewhere in the middle. which I believe
It's a problem for the
Yeah.
interpretation, right?
yeah, yeah. And maybe there's something about this figure I don't understand, but just looking at it, that's to me what it would imply.
Yeah, yeah. I have the same. They in the paper they do another figures, but it's the same. It's the same. That show the paper here. Okay, this is the figure that I just show you guys. You see, this is half of them are up and down, and then he do another type. This I think. In this one, most of them are up. Most of them are up. That's why it's not symmetrical anymore, the wave functions.
Mhm.
But still you have this problem here, right?
Yeah. And I don't know if the argument is, I'll have to read the paper, if it's that, the time scales they're showing here are really, really small. So there's no practical experiment that can show that. If you keep moving up in time, eventually all of them will be up or down. And maybe that's their claim. But I'll have to read it. Yeah.
It's almost like if you were assuming, the conventional interpretation is when you have a collapse to the state, it's instantaneous.
Yeah, in the orthodox interpretation.
If you did have their interpretation, which is a non-instantaneous collapse, this would be the kind of thing you'd expect.
Yes.
In the sense that you would eventually get to one or the other.
Yeah, but you have, if I understand, like if you have here, the spin is determined already in the beginning. You don't have a superposition in this interpretation.
Okay.
So initially it's like a little bit up, not totally up, like here. But after the time, so you have this.
Yeah, but I think Diego's point's interesting. It almost looks like it's slowly progressing towards an up or down state.
Yeah, because see here, initially it seems to be in the vertical, right? The horizontal.
Yeah.
And then they go up. Yeah. Yeah, you're right.
So the limit as time gets large, it goes to those states. But till you get there, there's some weirdness going on. Which means you don't have an instantaneous collapse. It's a gradual process.
Yeah. Yeah, seems to be here in the field, right? In the vector field.
Yeah,
So
you can see.
maybe that's why here in the middle you have like this indecision, because initially it's like in the horizontal, right?
Right.
And then you go up or down. Yeah, but in the idea I think is this. So the main difference is that so you don't have like the instantaneous collapse, but you have this like deterministic behavior here. So I'm not sure now if initially, in principle, I was thinking that was determined initially, but it seems I don't know if it is determined, but you don't know because the fluctuations of the field psi, because you don't know initially who is psi. I think it's this. So I think you don't know initially if they are up or down, but they are up or down initially. So you just don't know. So if you want to follow the trajectory, I think it could be something like that. But remember, you don't know all the initial data because you don't know the form of psi, the field psi.
I guess another question about that chart then would be, is that a mathematical model of what they think might happen? Or is that like in any way represented by any kind of experimentation?
Now this is mathematical.
Mathematical, okay.
Yeah. So because I didn't put all the math, it could be too tiresome. But he developed the method here. He used basically a Dirac equation. Free particle, let the initial state of the particle be a positive energy plane wave solution of free particle Dirac equation. And you write the equation this way, and then develop. In this section 3, he make the development of the theory. It's relativistic here. Relativistic energy. Yeah, I didn't check the details in the calculation because it's not the goal, at least not initially. Unless we are like convinced that this is the theory, so we goes deep in the calculations. So in principle, it's just the idea. Yeah, but it seems so to be a nice paper. I wish like in the next, I was thinking like you have another discussion about Bohm de Broglie to see, especially the criticism about this, because we are see the things that people is doing, but what about the criticism? And in the book that I suggest, like David Bohm, he make us, it seems he make a summary about some critics about the theory, and that I would like to discuss in the next round table. But yeah, what you guys think? More?
Yeah, still, I unfortunately I missed the. I connected at the beginning of the last meeting, but I had to disconnect. And one of the things I was curious about from 2 sessions ago is in this interpretation, it is said that the wave function is a real guiding wave, and then on top of that you have the particles. But I wonder, how do you define a particle, right? So in the standard interpretation of quantum mechanics, the particle is the wave function. But here, what is a particle? How is it defined? What's the size? What are some of the properties these particles have? And in your presentation today, I didn't see that either. So I wonder if anyone else looked into it.
Yeah, actually, when you asked this, I look for a better answer, but I didn't found. I remember you asked for what's the size of the electron, right? Exactly.
Mm-hmm.
And yeah, I didn't found. So I don't know if they have a solution for this.
Yeah. Yeah, because the way I understand, and correct me if I'm wrong, but the way I understand the way standard quantum mechanics works is, let's say you have a free electron and you prepare it in the form of a Gaussian wave packet, right? What is the size of that electron? It could be seen as an ill-posed question because it's a wave, right? It's not really a localized particle. So you could say, well, the size of that electron maybe is the envelope of that wave packet, but that really is telling you the uncertainty of where you're going to measure that electron, but not really the size of that electron. But at least you can formalize something about what the electron is, right? You can say, you can measure it in this location with this level of certainty. And to measure it, you would need to use, let's say, an electromagnetic wave. And then the frequency of that electromagnetic wave will give you the uncertainty of where that electron really is located. But you can't really say what the size is exactly, right?
Mm.
But in this interpretation, in the Bohm interpretation, they say that the electron is a particle, and it does have a size and maybe even a shape, right? What is the shape? Is it a sphere?
Yeah.
What is it?
Yeah.
Is it a string? So to me, that part is a little unclear.
Diego, it's almost like depends on almost what branch of physics you're looking at. I've seen papers where people talk about getting a better measurement on the size of the electron, and these papers are published like a year or two ago.
Hmm.
And one of the sides of these publications are that actually does have a shape, and it's a pretty good spherical shape. It's not a squishy sphere. It doesn't squish down to an ellipse really or something. It stays a sphere. And a lot of that comes out of guys who are looking at cosmology, because apparently the size of electron has an effect upon models of the creation of the universe and things like that. It's really bizarre. But that's an active area of research.
Yeah.
And guys in quantum mechanics saying it doesn't have a size, there's nothing to measure. And you got people on the other side are saying, yeah, we'll give you estimates and shapes.
But I think
on theory, right?
But I don't know if standard quantum mechanics really allows you to do that. I think maybe what you're looking at is what is the smallest size of the quantization of the electromagnetic field is that you can measure, right? That's different. That's not the size of the electron. That's the smallest resolution, let's say, you can get from the quantization or the quantization of the electromagnetic field. But the size of the electron in standard quantum mechanics depends on how you prepare that electron.
Okay.
Right? So I don't know. Maybe the answer is what you're saying. Maybe the answer to this the Bohm interpretation is that the size of the electron is the smallest unit you can possibly measure or something like that. But I've never seen it, so I'm curious how they were thinking about it. I think it's interesting.
Yeah, I never saw as well. At least not in the paper I saw about the Bohm. Could you share the papers you talk about, Bob?
Yeah, let me.
Oh,
I've got a really old one here. I'm going to put the link in. But I know there's more current stuff that updates this. So let me give you that one. And I'm looking at trying to look for the links to the papers right now.
I mean, to take it to the extreme.
That's a really old one. That's a 100-year-old paper, but still, that was like one of the first attempts. Let's see what else I can find.
To take things to the extreme, if you think about, a particle, let's say an electron in an infinite potential well, right? There is no sense of talking about the size of the electron there, because the electron in an infinite potential well is harmonics, which are sinusoid signals, right? It's sinusoid distributions, probability distributions. So the electron doesn't even have a size in that particular setup, right?
Yeah, I agree. It oscillates, right?
All right. Here's one on the shape. I'm giving the whole link. Hold on.
Oh, this is from Compton,
Yeah, 1990.
1990.
Yeah, it's a 100-year-old paper. Here's a more current thing about dealing with the measuring the shape of an electron.
Oh, I could. It didn't work here. I don't know if my connection, but this here is not working. Okay, so I'm thinking like in the next quantum T, like maybe we have like at least for now a last section about von der Broadway interpretation, and then we could like go to many words interpretation to start like discuss something. What you guys think? Or you think it's enough from von der Broadway for now? You guys know. Guys decide. I just try to prepare the material. Yeah, I would like to read a little bit about the criticism about von der Broadway, especially in the relativistic.
Yeah, yeah.
Yeah, go ahead.
Yeah, from my point of view, I'm okay either way. Like one more session on the criticisms, I will be okay with it. But if we want to move on, I think it should be fine too.
Okay, so I think one session for criticism. Then and you can return. I mean, in the future, it's not that we finish everything about the team. In the future, because the initial idea, I think, is see a little bit about the following the history, and in the future we can see like what people is doing like in modern days about these theories, these interpretations. So you see like many words and GWM discuss the Bell inequalities. I think important as well. See some experiments, and then we come to 21st century and see what people is doing now about this subject. Okay, so I think I'll stop sharing here the presentation. And in 15 days, maybe it's also, I think Bumblebee is not here today, but I think the schedule, I would like to know about you guys about the schedule, because it seems that the UK time will change, and the quantum team must be at 5 o'clock UK time. So when the change will be, I think the next will be 1 hour earlier. I think, I'm not exactly sure, but I want to know about you guys if it's okay, if it's 1 hour early, the next quantum T.
It still works for me 1 hour earlier.
And you, Bob?
Yeah, what time are you talking now?
Yeah, I think the next will be like 1 hour earlier. I think because the time will change in UK, and we are using like the UK.
Okay, so you're going back to what we used to have the old time. Your time
Yeah.
change catch. Yeah, that's fine with me. Noon is fine. Here.
Yeah, I don't know how Barry. I don't know if he's home.
Noon
Yes.
doesn't. Noon isn't good for me until May, but that's don't go by just me.
Oh, okay. Okay, good. So now I think for George is okay too. Visually, unfortunately, he lives. But I think for George is okay. I think 1 hour early. The people that usually appears live. So okay, and I hope some other people from YouTube that can't be in this time can be in the 1 hour early.
Mm.
So okay, so you guys have more comments, suggestions? Bob send the paper here, the link here. It's working this. So I think you could like stop here. Or George. Hi, George. Yes, no problem. I will stop recording, or otherwise the video will be too big.
Okay.
And we can talk after. Okay, so see you guys from YouTube. I believe the next one will be 1 hour earlier. So if you guys, if this time now 1 hour earlier is okay to be live, you guys can come. Welcome.
Can you change the invite for our calendars?
I think so. I think so. You say like in the.
I have something on my calendar that apparently came from you with the time, and it would be handy if that was changed so I don't have to worry about it.
Yeah. I think it will change because I think when the Bumble they put the time in the Google Calendar, the agenda, I think it's in the UK time. So when you change it there, change the, yeah. Okay, so I'll stop recording.